3 coronal mass ejections, each one a billion-ton blast of solar plasma, ripped from the far side of the sun, aimed straight toward one tiny interstellar intruder. 3. I. Atlas. And then silence. It didn't slow. It didn't swerve. It didn't even flinch. But the sun did. Solar activity spiked. Magnetic fields twisted. And yet the object's orbit? Perfect. Unshaken. How can something from another star system shrug off the full fury of our sun? Stay with me until the end. Because the data we're about to present suggests something unthinkable. 3. Atlas may not just be passing through our system, it may be testing it. If this mystery has you on edge, like it has me, make sure to hit like and subscribe, because you won't want to miss a single update as this unfolds in real time. Tell me where you're watching from, what time it is there, and what you think about this interstellar visitor. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. Right now, something is moving through the inner solar system that, theoretically, shouldn't exist. I don't mean it shouldn't be here, traveling through our cosmic neighborhood, on a trajectory from somewhere unimaginably distant. We've seen interstellar visitors before. I mean, it shouldn't possibly behave the way it's behaving, because according to every model we have, every equation we trust, every principle of orbital mechanics and plasma physics that governs how objects move through space, 3I Atlas should have been deflected. It should have been pushed, even slightly, off its predicted course when the sun threw everything it had at this thing, but it wasn't. Let me back up for just a moment so you understand exactly what we're dealing with here. On July 1st, 2025, the Atlas Survey Telescope in Chile picked up a faint smudge moving against the background stars. Nothing unusual. Telescopes find objects all the time, but within hours, astronomers realized this wasn't just another comet or asteroid making its routine lap. The orbit was wrong, wildly wrong. The trajectory wasn't an ellipse, bringing it back someday. It was a hyperbola, an escape curve, the mathematical signature of something that came from outside and is just passing through. This was the third confirmed interstellar object ever detected, and they gave it a designation that sounds more like a cipher than a name. 3. Atlas. Now, this is where things get interesting in that special way that makes astronomers lose sleep. When they calculated its orbit with increasing precision over the following weeks, they found an eccentricity of around 6.1, maybe 6.2. For reference, anything above 1 means the object isn't bound to our Sunday, but 6? That's an absurdly hyperbolic number. This thing is moving at roughly 60 kilometers per second relative to the sun's rest frame, which means when it finally leaves our solar system, it'll still be traveling at that breakneck speed into the darkness between stars. It came from somewhere out there, in the galactic thick disk, potentially billions of years old, potentially older than our entire solar system, and it's just cutting across on a one-time visit. The European Space Agency and various observatories tracked it meticulously. They calculated it would reach perihelion, its closest approach to the Sun, in late October 2025, just inside the orbit of Mars at about 1.35 astronomical units, close enough to heat up significantly, far enough to avoid vaporizing. The Hubble Space Telescope got a good look at it on July 21st, 2025. The images showed a classic cometary structure, a nucleus surrounded by a glowing coma, a tail being blown back by solar radiation and the solar wind. Spectroscopy from the James Webb Space Telescope revealed something unexpected. The gas coming off this thing, unusually rich in carbon dioxide. Not the water and carbon monoxide mix we see in most comets. Carbon dioxide. That tells us something about its chemical composition, its thermal history, maybe the conditions in whatever stellar nursery spawned it billions of years ago. Then, 3I Atlas did something that made tracking it extremely difficult. It passed close to Mars on October 3rd, close enough that spacecraft orbiting the red planet, like the ExoMars Trace Gas Orbiter, captured imagery confirming its position right where the prediction said it would be. No deviations, no surprises. But after that Mars encounter, from Earth's perspective, the object moved behind the Sunday Superior Conjunction, astronomers call it. When something passes on the far side of the Sun relative to Earth, you can't see it through regular telescopes anymore. The object vanishes behind a wall of light. This is where coronagraphs become essential. These are specialized instruments designed to block out the Sun's disk so you can observe the area immediately around it, the corona, the solar wind, and anything else moving through that region. Satellites like GOES-19 carry coronagraphs, and this is where independent observers, amateurs, and professionals alike started reporting something extraordinary. They claimed they could see 3I Atlas, faint but detectable, moving through the coronagraph frames exactly where the predicted ephemeris said it should be. Frame by frame, this tiny smudge crept along its calculated path through one of the most hostile environments in the solar system, the immediate vicinity of our actively erupting star. And that's when the Sun decided to make things interesting. According to reports emerging from people analyzing coronagraph data and solar weather logs, 3 massive coronal mass ejections, CMEs, launched in rapid succession from the far side of the Sunday, not from regions facing Earth, which is why most people didn't hear about them, but from the far side. And here's the critical detail. The timing and trajectory of these CMEs aligned with the predicted position of 3I Atlas. Picture a plasma cannon firing 3 times in quick succession, each burst containing billions of tons of magnetized solar material traveling at hundreds or thousands of kilometers per second, all converging on a tiny interstellar interloper barely a few kilometers across. A coronal mass ejection isn't just a puff of hot gas. It's a wall of ionized particles, magnetic field lines twisted into chaotic knots, electromagnetic forces on scales that dwarf anything we can produce on Earth. When a CME hits a comet, it can strip away parts of the coma, compress the tail, create shock waves. And if the momentum transfer is significant enough, if enough of that kinetic energy couples into the nucleus itself, it must alter the orbit. Even slightly, a tiny deviation that would only show up as a small discrepancy from the predicted path over days or weeks. But it must happen. Except it didn't. The object that emerged from behind the Sun in the coronagraph imagery, the faint smudge that continued along its trajectory after those 3 CMEs supposedly slammed into it, was exactly where the original ephemeris predicted it would be. No deflection, no deviation, no measurable change in velocity or direction. As if those CMEs, those gargantuan eruptions of solar fury, had simply passed through it or around it, without imparting any momentum at all. Which brings us to a hypothesis that sounds like science fiction, but is being discussed in certain circles with increasing seriousness. What if 3I Atlas isn't just passively drifting through the Sun's magnetic field? What if it's interacting with it? What if this object, with its dusty coma and plasma envelope, is somehow short-circuiting the Sun itself, creating a feedback loop where its presence triggers electromagnetic disturbances in the solar atmosphere, and those disturbances manifest as CMEs directed back at the very object causing them? And what if that same electromagnetic coupling acts as a kind of shield or stabilizer, preventing the CMEs from deflecting it the way simple Newtonian mechanics would predict? I know how that sounds, but stay with me, because if there's even a kernel of truth to this idea, we're not just looking at a weird comet. We're looking at something that could force us to rewrite our understanding of how interstellar objects interact with stars, how plasma physics operates on scales we've never observed before, and maybe, just maybe, what kinds of structures or compositions could exist in objects wandering between the stars. Because whatever 3I Atlas is, it's not behaving like anything we've seen before. And that means everything we thought we knew about objects like this might be incomplete. So, let's unpack this mystery piece by piece, test the theories, examine the evidence, and explore some wild, but just barely plausible scenarios. because something hit 3I Atlas with the force of a solar storm, and it didn't budge. And we need to figure out why. We need to establish exactly what we know about 3I Atlas before we dive into the truly strange parts of this story. Because the foundation here, the observational record, is actually quite solid, even if the interpretation is about to get weird. When the Atlas Survey Telescope in Chile first spotted this object on July 1st, 2025, it appeared as nothing more than a faint dot moving slowly against the fixed stars. But within 24 hours, as other telescopes around the world picked it up and added their measurements, the orbit calculators started spitting out numbers that made people sit up and take notice. The eccentricity came back around 6.1 to 6.2. In orbital mechanics, eccentricity measures how elliptical or circular an orbit is. 0 is a perfect circle. Values between 0 and 1 describe ellipses. Exactly, 1 is a parabola. Anything above 1 is a hyperbola, an open curve that never closes, never comes back. An eccentricity of 6 means this object is moving so fast that the sun's gravity barely even curves its path. It came from interstellar space, traveling at about 60 kilometers per second, and when it leaves, it'll still be moving at roughly that speed. The sun just gives it a gravitational assist, bending its trajectory slightly, but ultimately, it's just passing through. The Virtual Telescope Project and other observatories quickly refined the trajectory. Perihelion, the closest approach to the Sun, was calculated for late October 2025 at a distance of approximately 1.35 astronomical units. 1 AU is Earth's average distance, so 1.35 AU puts perihelion just inside Mars's orbit. The really crucial data came on July 21st, 2025, when the Hubble Space Telescope turned its instruments toward 3I Atlas and captured high-resolution imagery. What Hubble saw was a classic cometary structure, a central nucleus surrounded by a diffuse coma of gas and dust, and a tail streaming away from the Sunday. Hubble's measurements allowed astronomers to constrain the size of the nucleus. Based on brightness, they estimated the nucleus was probably no larger than about 2.8 kilometers in diameter. Fairly small, but massive enough to produce the coma and tail structure they were observing. Then came the James Webb Space Telescope's contribution. JWST can do spectroscopy that Hubble can't match, breaking down the light from the coma to identify specific molecules. And what JWST found was unusual. The coma was dominated by carbon dioxide, not water vapor, which is the primary volatile in most comets from our solar system, not carbon monoxide, carbon dioxide, CO2. That tells us something profound about this object's composition and thermal history. It's compositionally distinct from the typical comets we see in our own Oort cloud or Kuiper belt. Now we get to October 3rd, 2025. 3I Atlas made a close approach to Mars. This was observational luck because multiple spacecraft orbiting Mars, including the ExoMars Trace Gas Orbiter, operated by the European Space Agency, were positioned to observe the object as it flew past. They captured images confirming its position and velocity. The data showed no deviation from the predicted trajectory. This is important because it establishes a baseline. As of early October, before the object moved behind the Sun, its orbit was exactly where the calculations said it should be. No surprises, no unexplained accelerations or decelerations. Then came the conjunction. As 3I Atlas continued inward toward perihelion, its position in the sky moved closer and closer to the Sun as seen from Earth. By mid-October, it had effectively disappeared into the solar glare. Normal optical telescopes were useless at this point. You need specialized equipment designed specifically to block out the Sun's disk. This is where coronagraphs become essential tools. A coronagraph uses an occulting disk to block the light from the Sun's photosphere, revealing the much fainter corona and the space immediately around the Sunday. Satellites like GOES-19, positioned in geostationary orbit, carry coronagraphs for monitoring solar wind and CME activity. The Solar and Heliospheric Observatory SOHO has been doing this for decades, and this is where independent observers started reporting detections. People analyzing publicly available coronagraph imagery claimed they could see a faint object moving through the frames in late October 2025, right around the time 3I Atlas was supposed to be near perihelion behind the Sunday. The object's motion matched the predicted ephemeris. Its brightness was consistent with a small nucleus reflecting sunlight at that distance. Frame by frame, day by day, the little smudge crept along exactly the path that had been calculated months earlier. No deviation, no surprise accelerations, just the smooth, predictable arc of an object following Newton's laws and Kepler's equations. But here's where the story takes its first sharp turn into the strange. During that same period, while 3I Atlas was behind the Sun, solar observatories recorded something unusual. 3 large coronal mass ejections erupted in quick succession from active regions on the far side of the Sunday. The far side, meaning the hemisphere facing away from Earth. These weren't Earth-directed CMEs, which is why they didn't make the news. But according to reports now emerging, the timing and geometry of these eruptions aligned disturbingly well with the predicted position of 3I Atlas. Think about the geometry for a moment. Earth is on one side of the Sunday. 3I Atlas is passing near perihelion on the opposite side. An active region on the far side of the Sun erupts, launching a CME outward in the general direction where 3I Atlas happens to be at that moment. Then it happens again, and again. 3 times. 3 massive bursts of magnetized plasma, each one containing perhaps billions of tons of material, and all 3 aimed, whether by coincidence or something stranger, in the direction of a tiny interstellar visitor. So the question becomes, did those CMEs hit 3I Atlas, or pass near it, or interact with its coma? And if they did, why didn't we see any deviation in the orbit? Because that's the real mystery. The coronagraph observations that came after the conjunction show the object exactly where it was supposed to be, no deflection, which means either the CMEs missed it entirely, or something is very wrong with our understanding of how CME impacts should affect small bodies. And that's where this story stops, being a simple tale of tracking an interstellar comet, and starts becoming something much more troubling and fascinating. We need to talk about what a coronal mass ejection, a CME, actually is. Because the term gets thrown around a lot in space weather reports, but most people don't grasp the sheer scale and violence of these events. A CME is not a solar flare, though the two often occur together. A solar flare is a burst of electromagnetic radiation. It travels at the speed of light. A CME is different. A CME is a physical eruption of plasma, a chunk of the sun's corona being violently expelled into space, carrying tangled magnetic field lines within it. When a CME launches, billions of tons of ionized hydrogen and helium blast outward from the sun at velocities that can range from a few hundred kilometers divided by s to over 3,000 kilometers per second for the most extreme events. This isn't just hot gas, it's magnetized plasma. Now, imagine what happens when a CME encounters a small body, like a comet. The comet has no global magnetic field like Earth, no protective magnetosphere. It's just a solid nucleus, maybe a few km across, surrounded by a diffuse coma. When the CME arrives, the first thing that happens is a shock wave. The leading edge of the CME compresses the ambient solar wind. This creates a pressure wave that can compress the coma, brighten the plasma tail, and potentially strip away outer layers of gas and dust. But here's the critical question. Can a CME deflect a comet's orbit? Basic physics says yes, it should be possible. The momentum carried by billions of tons of plasma moving at hundreds or thousands of km divided by s is substantial. If even a fraction of that momentum transfers to the solid nucleus of the comet, you'd expect some change in velocity. It might be small, maybe only a few meters divided by s. but it should be measurable over time as the comet's position drifts away from the predicted ephemeris. Let's put some rough numbers to this. Assume a typical large CME contains about 10 to the 16th grams of material, that's 10 trillion kg, traveling at, say, 1,000 kilometers per second. Momentum is mass times velocity. Now assume 3. I Atlas has a nucleus with a radius of about 1.4 kilometers, from Hubble's 2.8 kilometers diameter. If it's made of typical cometary material, that gives a mass of roughly 6 trillion kg. If the CME hits it head-on, and even 1% of the CME's momentum transfers to the nucleus, you get a velocity change on the order of maybe 20 meters per second. 20 meters per second doesn't sound like much, but over days and weeks, that compounds. The comet's position would shift noticeably from its predicted path. Observers tracking it would see it arrive at perihelion slightly early or late. Astrometric measurements should be able to detect deviations of that magnitude. So, if 3 CMEs hit 3I Atlas, each potentially transferring momentum, we should see evidence of deflection. The orbit should change. But according to those coronagraph observations, it didn't happen. The object stayed on course. Which brings us to 3 possibilities. First, maybe the CMEs missed it entirely, passing nearby but not actually intersecting the nucleus or even the inner coma. Space is big. Maybe 3I Atlas was off to one side of the main plasma stream. Maybe it didn't get hit hard enough. Second possibility. Maybe our estimates are wrong. Maybe the nucleus is much more massive than we think, dense enough that the momentum transfer was negligible. But that would require densities far higher than typical cometary material, more like rock or even metal. And there's no indication it's a solid iron cannonball. Third possibility, and this is where things get genuinely weird. Maybe something about 3I Atlas prevented the momentum transfer. Maybe its coma has properties that shield the nucleus. Or maybe there's an electromagnetic interaction happening that we don't understand. Something that couples the CME's energy into the plasma environment around the object without translating into a net push on the solid nucleus itself. This is the short-circuiting hypothesis, and we're going to examine it in detail because it's simultaneously the most speculative and the most intriguing explanation. But first, let's nail down the timeline and the evidence. The CMEs in question allegedly erupted in late October 2025, around the time 3I Atlas was near perihelion. Solar weather archives should contain records of these events. The problem is, far-side CMEs are harder to characterize. We rely on helioseismology, using sound waves traveling through the sun to infer activity on the hidden hemisphere, and data from spacecraft off to the sides like stereo. So the evidence for these specific CMEs may be indirect or incomplete. What we do know is that active regions rotate with the sun. An active region on the far side today will rotate into view in about 2 weeks. If there was unusual activity on the far side in late October aimed at 3I Atlas, those same active regions should have rotated into Earth-facing view in mid-November. Did they produce more eruptions? Did they show signs of being particularly large or energetic? And then there's the geometry. But here's what troubles me. The coronagraph detections showing 3I Atlas exactly on track after the alleged CME impacts are hard to dismiss. If those observations are accurate, and if CMEs did intersect the object's path, then we have a genuine puzzle. Either the object is far more massive than it appears, raising questions about what it's made of, or something more exotic is going on. And that brings us to the hypothesis that sounds like it belongs in a science fiction novel, but is starting to gain traction. The idea that 3I Atlas is electromagnetically interacting with the sun in a way we've never observed before, that it's somehow triggering the very CMEs being launched toward it and simultaneously shielding itself from their effects. A cosmic feedback loop, a short circuit between star and interloper. Let me introduce you to an idea that's going to sound completely absurd at first, but bear with me, because once you understand the physics involved, it becomes just barely plausible enough to be worth taking seriously. The hypothesis goes like this. 3I Atlas is not just passively moving through the sun's magnetic field and solar wind. Instead, it's actively interacting with the sun's electromagnetic environment, creating disturbances in the local plasma, modifying current flows and magnetic field line topology in ways that feed back to the sun itself. And those feedback effects, according to this hypothesis, can trigger the release of stored magnetic energy in the solar corona, manifesting as coronal mass ejections, aimed back toward the very object, causing the disturbance. It's a kind of electromagnetic coupling between object and star, a circuit where the object acts as a perturbation, and the sun responds by short-circuiting, dumping energy in the direction of the disturbance. I know it sounds crazy, but let's break down the physics piece by piece. Start with what we know about how comets interact with the solar wind. A comet approaching the sun sublimates volatiles, creating a coma. That neutral gas gets ionized by ultraviolet light from the sunday. Once ionized, they become charged particles, and charged particles respond to electromagnetic fields. The solar wind is a plasma, an ionized gas threaded with magnetic field lines. When the cometary ions interact with the solar wind, they get picked up by the magnetic field and carried downstream, forming the classic plasma tail. This interaction creates a region around the comet. There's a bow shock upstream. Spacecraft have flown through cometary plasma environments and measured these structures directly. We know they exist. We know they involve currents and magnetic fields. What we don't normally see is any evidence that these local interactions feed back to the sun in a significant way. The comet is a tiny perturbation in a vast system. But what if 3I Atlas is different? What if its coma is unusually dense or conductive? What if it has properties that make it a particularly strong current carrier? One possibility is that the object might contain conductive material in its nucleus or dust grains, perhaps metal or carbon compounds, that enhance the electrical conductivity of its coma. Another possibility is that the unusual CO2-rich composition creates a plasma environment with different properties than typical water-rich comets. Then there's the question of scale. 3I Atlas is moving at 60 kilometers per second relative to the sunday. That's fast, much faster than most comets. High velocity means the object is cutting through magnetic field lines at high speed, potentially inducing larger electric fields through Faraday's law of induction. Moving a conductor through a magnetic field generates an electromotive force. Now, here's where we venture into more speculative territory. The sun's corona is a magnetically dominated plasma environment. These field lines can store enormous amounts of energy when they're twisted or sheared. Sometimes that stored energy is released suddenly through a process called magnetic reconnection. This is what powers solar flares and CMEs. The hypothesis, then, is that 3I Atlas could act as a trigger for magnetic reconnection. Maybe its plasma environment perturbs the local field structure just enough to bring oppositely directed field lines into proximity. Maybe currents flowing through its coma provide a conductive channel that facilitates reconnection. Maybe its presence creates a magnetic anomaly that destabilizes an already stressed coronal magnetic structure. If any of this happens, the result could be a CME launched from the region of disturbance in the direction of the object itself. And here's the kicker. If the CME is triggered by the object, and if the object has some kind of electromagnetic shielding or current balancing effect, then you'd observe exactly what the coronagraph data shows. CMEs aimed at the object, but no orbital deflection. The object triggers the gun pointed at itself, but the bullet passes through or around it without pushing it. This sounds like science fiction. I'll grant you that, but let me give you some context. There's a scientist named Hannes Alfvén who won the Nobel Prize in 1970 for his work on magnetohydrodynamics. Alfvén was one of the pioneers of plasma cosmology, and he argued that electromagnetic forces play a much larger role in astrophysical systems. He talked about electric currents in space, about how plasma doesn't always behave like a neutral gas, but has collective behaviors driven by long-range electromagnetic interactions. Now, most of Alphen's specific ideas didn't gain traction, but the core insight that plasmas can exhibit non-local, electromagnetically dominated behavior is solid physics. And if you're willing to entertain the possibility that an interstellar object with unknown composition might interact with the sun's magnetic field in unusual ways, then you're operating in a regime where Alphen's kind of thinking becomes relevant. Mainstream solar physics would say no, the scales don't match. But what if the object is acting more like a catalyst than an energy source? What if it's not providing the energy for the CME, but just providing the trigger that releases energy already stored in the coronal magnetic field? In that case, you wouldn't need the object to be electromagnetically powerful. You just need it to be in the right place, at the right time, with the right properties, to tip a metastable system over the edge. And then there's the shielding question. How could an object avoid being deflected? One possibility is geometric. If the coma is large enough and diffuse enough, the CME's momentum might be absorbed by the coma without reaching the nucleus. Another possibility is electromagnetic. If currents induced in the coma create their own magnetic fields, those fields could interact with the CME's magnetic structure in ways that redirect or balance the forces. Imagine the coma acting like a magnetic sail. These are all speculations, stacked on speculations. But here's why I'm spending time on this. If there's even a small chance this hypothesis has merit, it would revolutionize our understanding. It would mean that interstellar objects aren't just passive test particles, but active participants in the electromagnetic ecology of the systems they pass through. It would open up entirely new questions. And it would mean that 3I Atlas, this tiny visitor from the void, might be the key to unlocking a new branch of astrophysics we didn't even know was missing. Let's get quantitative for a moment, because we need to understand just how surprising it is that 3I Atlas apparently didn't budge when those CMEs hit. To do that, we need to work through some basic orbital mechanics and figure out what kind of deflection we should expect, then compare that to the observational constraints. Start with the object itself. Hubble observations suggest the nucleus is no larger than 2.8 kilometers in diameter. Let's assume it's roughly spherical for simplicity and work out its mass under different density assumptions. If it's made of typical cometary material, low-density water ice and dust with lots of porosity, the bulk density might be around 0.5 grams per cubic cm, similar to Comet 67P. With a radius of 1.4 kilometers, you get a mass of roughly 5.5 x 10 circumflex 15 grams, or 5.5 trillion kg. Now, recall our calculation from part 3. A head-on impact from a strong CME could easily impart a velocity change around 20 meters per second. That should have been detectable, as the positional deviation accumulates over time, but it wasn't. So, what are the conventional explanations? First possibility. Maybe the nucleus is much more massive than we estimated. If the density is higher, say 2 or 3 grams per cubic centimeter like solid rock instead of fluffy ice, then the mass goes up by a factor of 4 to 6. That would reduce the expected velocity change proportionally, down to maybe 10 meters per second or less. Still detectable. If the nucleus is even denser, maybe a fragment of some ancient protoplanetary core with metallic content. But here's the problem. If the nucleus is that dense, why is it producing such an active coma? Dense objects typically have lower volatile content. Yet, we see a clear coma and tail in the Hubble images, and JWST spectroscopy shows active CO2 emission. It doesn't fit. Second possibility, maybe the CMEs, mostly missed. The nucleus is tiny, only a few kilometers across. The coma is much larger, extending tens of thousands of kilometers, but mostly empty space. If the bulk of the CME's momentum was carried in a concentrated stream that happened to pass to one side of the nucleus, most of the momentum would blow through the coma without hitting anything solid. The coma might light up, the plasma tail might compress, but the nucleus wouldn't feel much push. This, actually, is quite plausible. CMEs aren't uniform density clouds. They have structure. If 3I Atlas got lucky, the deflection could be negligible. Third possibility. Maybe the geometry was such that multiple impacts cancelled out. If 3 CMEs hit from slightly different directions, their momentum vectors might partially cancel. This seems unlikely, given that all three allegedly came from similar source regions on the far side of the Sun. But here's where things get interesting. None of these conventional explanations really satisfies me, because they all require fortunate coincidences or fine-tuning. The object would have to be denser than it appears, and the CMEs would have to miss by just the right amount, or the impacts would have to cancel in a very specific way. Any one of these could be true, but when you stack multiple unlikely coincidences together, you start wondering if maybe there's a simpler explanation involving something we don't understand. So let's revisit the exotic hypothesis: electromagnetic shielding or momentum redistribution. Suppose the coma of 3I Atlas has properties that allow it to interact with the CME's magnetic field in a way that redirects or absorbs the momentum without transferring it to the nucleus. How might that work? One mechanism is magnetic pressure. The CME carries magnetic field lines. If the coma also has an internal magnetic structure, then the two magnetic fields can push against each other. The force is distributed over the volume of the coma. It could act like a magnetic cushion, spreading the CME's impact. Another mechanism is current flow. If the interaction induces strong electric currents in the coma, those currents interact with magnetic fields via the Lorentz force. The force can act in any direction. If the induced currents are distributed symmetrically, they could generate forces that partially cancel the direct momentum transfer. A third mechanism, more speculative still, is that the object itself has a conductive core or internal structure that generates its own magnetic field. If the nucleus is partially metallic, it could generate a magnetic field like Earth does, only much weaker, interacting with external plasma. This sounds far-fetched for a comet, but remember, we're talking about an interstellar object that might be billions of years old. But here's what I find compelling. The mere fact that we're having this discussion means 3I Atlas is pushing the boundaries of our understanding. Even if the exotic hypotheses turn out to be wrong, the exercise of working through them teaches us something about the limits of our models. So, what does it mean that 3I Atlas didn't budge? It means either we're missing something in our observations, or we're missing something in our models, or we're missing something in our understanding of what kinds of objects can exist in the universe. And any of those possibilities is worth investigating further, because that's how science advances. By confronting observations that don't quite fit, and refusing to look away until we understand why. Before we go any further down the rabbit hole with 3I Atlas, we need to put this object in context. By comparing it to the other confirmed interstellar visitors we've detected, because the truth is, we're still in the very early days. And every single one so far has been weird in its own way. Understanding those weirdnesses might help us figure out whether 3I Atlas is uniquely strange, or just the latest in a series of cosmic oddities forcing us to expand our taxonomy. Let's start with 1I, Oumuamua. Discovered in October 2017, Oumuamua means scout or messenger from the distant past. And it was an apt name, because this object was like nothing we'd ever seen. Its orbit was hyperbolic, eccentricity around 1.2, clearly from interstellar space. But what made Oumuamua truly bizarre was its lack of visible coma or tail, despite passing quite close to the Sun, combined with an unexpected non-gravitational acceleration as it moved away. Non-gravitational acceleration is common in comets. Outgassing acts like a tiny rocket engine, but Oumuamua accelerated without any detectable outgassing. What was pushing it? Hypotheses were proposed. Maybe it was outgassing pure nitrogen ice? Maybe it was an artificial object, a light sail from another civilization? That last hypothesis, championed by Avi Loeb, remains controversial, but it sparked important discussions. Then came 2I, divided by Borisov. Discovered in August 2019 by an amateur astronomer, Borisov, compared to Oumuamua, was almost refreshingly normal. It looked like a comet. It acted like a comet. It had a clear coma and tail, and spectroscopy showed familiar cometary molecules like water and carbon monoxide. Its orbit was hyperbolic, eccentricity around 3.4, but its behavior was conventional. Borisov proved that interstellar comets can be similar to our own solar system's comets. Now, we have 3I Atlas. With its eccentricity of 6.1, its CO2-rich coma, its apparent electromagnetic interaction with the Sun, and its mysterious resistance to deflection, how does it compare? Let's break it down. Velocity. All three are hyperbolic, but 3I Atlas is moving fastest at infinity, about 60 kilometers per second, compared to Oumuamua's 26 kilometers per second and Borisov's 32 kilometers per second. That higher velocity suggests it may have originated from a different region of the galaxy, possibly the galactic thick disk, an older stellar population. Size. 3. I Atlas appears to be the largest of the three, maybe 2 to 3 kilometers, compared to Borisov around half a km, and Oumuamua estimated at only a few hundred meters. And here's another thought. Maybe the key is the activity level. Borisov was very active, outgassing strongly. Oumuamua was inactive, just a bare surface. 3I Atlas is actively outgassing, but maybe not as vigorously as Borisov. If the coma density is in some intermediate range, not too thick and not too thin, maybe that's the sweet spot, the Goldilocks zone. Where electromagnetic effects become important, too little gas, and you don't have enough plasma to interact. Too much gas, and the interaction is dominated by collisional drag. The Goldilocks zone for plasma interactions might require just the right level of outgassing, or maybe, and this is the possibility that keeps me up at night, maybe weird is normal for interstellar objects. Maybe objects that have been wandering the galaxy for billions of years, exposed to cosmic rays, occasional stellar encounters. Maybe they evolve in ways that our solar system's comets don't. Maybe they develop properties, structures, compositions that we can't replicate here. If that's true, then 3I Atlas isn't just a comet from another star system. It's a time capsule from an earlier epoch of galactic evolution, a sample of matter formed under different conditions, and if it's interacting with our Sun in ways we've never observed before, that's not just a curiosity. It's a window into physics we've never had a chance to study. So, where does this comparison leave us? It tells us that 3I Atlas is unusual, even among interstellar objects. But it also tells us that unusual might be the norm. It suggests that the short-circuiting hypothesis, while exotic, isn't completely out of left field. When you consider that we've seen one object with unexplained acceleration, and now we might be seeing another with unexplained electromagnetic behavior. Let's talk about what we don't know. Because in science, acknowledging the gaps in your data is often more important than celebrating what you think you figured out. And when it comes to 3I Atlas and this entire story about CME impacts and electromagnetic interactions, there are some significant gaps. There are hints of information that might exist, but isn't publicly available, and questions about whether we're working with the complete picture or just the fragments that have made it into the public domain. Start with what we do have. The discovery announcement came quickly after Atlas detected it on July 1st. That's standard procedure. Hubble observations on July 21st were released through NASA. James Webb spectroscopy, showing the CO2 composition, released through NASA Goddard. Spectroscopic observations from the Gran Telescopio Canarias, published in Astronomy and Astrophysics. All of that is public, peer-reviewed, or at least officially released through established channels. You can look up the papers. That's how science should work. transparency, public scrutiny. But here's where it gets murky. The claims about CMEs hitting 3I Atlas and the object not budging are not, as far as I can tell, in any peer-reviewed publication yet. They're emerging from analysis of coronagraph imagery, possibly by independent researchers or amateur astronomers who have access to publicly available data from solar observatories. That doesn't automatically make the claims false. Gennady Borisov discovered 2I divided by Borisov with a homemade telescope. But it does mean we need to be cautious about accepting claims that haven't been vetted through peer review, especially when those claims are extraordinary. So, what data might exist that we don't have access to? First, high-cadence coronagraph observations. Instruments like OnGo's 19 and SOHO take images continuously, but not all of those images are processed publicly in real time. There's often a delay. Coronagraph images are optimized for detecting CMEs and monitoring the corona, not for tracking faint comets. Extracting a comet's position from those images requires specialized work, and it might not have been done yet by official teams. Second, in situ plasma measurements. This is a big one. Various spacecraft in the inner solar system carry instruments that measure the local plasma environment, particle density, velocity, magnetic field. Parker Solar Probe, Mars orbiters, if any of these spacecraft happen to be positioned to sample the plasma downstream of 3I Atlas, that data would be incredibly valuable. But spacecraft data often has an embargo period. Mission teams get exclusive access for months or even years. That data might exist. It might show something interesting. But we won't know until it's released. Third, far side solar observations. We don't have a spacecraft on the far side, but we do have helioseismology techniques and data from stereo. If there were major active regions on the far side in late October, capable of producing multiple large CMEs, there should be some evidence. But, again, has anyone specifically looked for this? Has anyone correlated far-side active regions with the dates and geometry needed to target 3I Atlas? That kind of detective work requires time, and if nobody's funding it, it won't get done. Let me be clear. I'm not suggesting a conspiracy or cover-up. I don't think anyone is hiding evidence of alien technology. What I am suggesting is that the scientific process is messy and slow. Data doesn't flow instantly. And there are legitimate reasons why we might not have the full picture yet. But that also means we need to be humble. When someone says 3I Atlas didn't budge, we should ask, how do they know? What's the measurement precision? What are the error bars? Has this been independently verified? And when someone proposes an exotic hypothesis like electromagnetic short-circuiting, we should ask, what specific predictions can we test with future data? This is why this story is worth paying attention to. Even if the exotic hypothesis turns out to be wrong, the exercise of working through it reveals gaps in our data that we should fill. The hidden data problem is both a challenge and an opportunity. It's a challenge because it means we can't definitively answer right now. But it's an opportunity because as more data becomes available, as more researchers dig into this story, we'll gradually build a more complete picture. And that picture might surprise us. It might confirm conventional explanations, or it might reveal something genuinely new. We've been operating under an assumption that 3I Atlas is essentially a comet, an icy body with volatiles, sublimating when heated, producing the coma and tail we observe. And maybe that's correct. Maybe it is just a comet, albeit one with unusual composition. But let's step back and ask a more fundamental question. What if our classification is wrong? What if 3I Atlas is something else entirely? Something that happens to look like a comet, but has a fundamentally different structure or origin. This is where we need to expand our taxonomy of possible object types. When we think about small bodies, we categorize them as asteroids, comets. But that classification scheme is built on decades of observing objects in our solar system. Objects formed in the same protoplanetary disk. Interstellar objects don't have to follow those rules. They could come from systems with different elemental abundances, different formation temperatures. They could represent object types that simply don't exist in our solar system. Let me walk you through some possibilities. Exotic, but not impossible. First, what if 3I Atlas is a fragment of a disrupted exoplanet? Imagine a rocky world, maybe something like Earth, billions of years ago. Something catastrophic happens, maybe a giant planetary collision, maybe gravitational perturbations from a passing star tear it apart. The fragments get ejected into interstellar space. A fragment of a planetary core would have very different properties. It might be much denser, with rock and metal dominating instead of ice. But if that core fragment also had volatiles trapped inside, maybe from the original planet's mantle, those volatiles could be released when the object heats up. You'd see outgassing and a coma, mimicking cometary behavior. But the nucleus itself would be far more massive, far denser. That higher density would make it much more resistant to deflection by CME impacts. The momentum transfer calculations we did assumed cometary density around 0.5 grams per cubic cm. If the actual density is 5 or 8 grams per cubic centimeter, like solid iron, the expected deflection drops proportionally. This scenario could also explain the CO2-rich composition. Carbon dioxide can be trapped in minerals. Second, what if it's an ancient object from the very early galaxy? Formed when metallicity was much lower than today, objects formed around second-generation stars would have different elemental ratios. Maybe that ancient chemistry includes unusual minerals, giving it electromagnetic properties we don't see in younger objects. Third, and this one is going to sound wild, what if 3I Atlas has a conductive core that acts like a natural electromagnet? Certain iron meteorites found on Earth contain iron-nickel alloys that can hold remnant magnetization. If an object formed in a strong magnetic field environment, it could acquire a frozen-in magnetic field that persists for billions of years. Now, if 3I Atlas has a metallic core with remnant magnetization, that field could interact with the Sun's magnetic field and the CME's magnetic structure, providing exactly the kind of electromagnetic shielding or force redirection that would prevent orbital deflection. Is there any evidence? Not directly, but remember the polarization measurements published in Astronomy and Astrophysics? The paper noted unusual deep negative polarization. This can indicate something about the dust grains. If the dust grains contain metallic inclusions, maybe there's a metallic core in the nucleus. Fourth, what if it's not a single object, but a rubble pile? Many asteroids are thought to be rubble piles, held together by weak gravity. If 3I Atlas is a rubble pile, with lots of void space, when CMEs impact, the forces might be absorbed by the outer layers, protecting the core and preventing net momentum transfer. Fifth possibility, and I'm going to say this even though I know how it sounds, what if it's artificial? What if 3I Atlas is not a natural object at all, but a probe, an artifact, constructed by some other civilization billions of years ago and sent wandering through the galaxy? This is the hypothesis that got so much attention with Oumuamua, and while I personally think it's extremely unlikely, I can't completely dismiss it without evidence. If it were artificial, if it had some kind of propulsion or magnetic shielding technology, that could explain both the lack of deflection and the electromagnetic interactions with the Sunday, An advanced civilization might design an interstellar probe to withstand close stellar encounters, to use stars for gravitational assists, or even to harvest energy from stellar magnetic fields. All of these exotic possibilities, from planetary fragments to ancient objects to artificial probes, they all make different predictions. A dense fragment should have a high mass. An ancient object might have weird elemental ratios. A magnetized core should create detectable effects. The way forward is obvious. Gather more data. But until then, the most reasonable approach is to assume 3I Atlas is a natural object, but with properties that challenge our current understanding. We don't need it to be artificial for it to be scientifically important. Weird natural phenomena are exciting enough on their own. Now, we're going to venture into territory that's even more speculative and controversial than anything we've discussed so far. Because the claims about 3I Atlas don't stop with electromagnetic interactions and lack of deflection, some people are suggesting there's a broader connection between this object, solar activity, and even conditions here on Earth. Specifically, they're claiming that the same active regions that launched CMEs toward 3I Atlas are rotating into Earth-facing positions, potentially coinciding with a supermoon or full moon, and that this combination could trigger enhanced geomagnetic activity or even seismic events. Let me be absolutely clear before we dive in. This chain of causation from interstellar object to solar eruption to Earth-directed space weather to earthquakes is extremely speculative and not supported by mainstream scientific consensus. But it is being discussed, and I think it's worth examining both the tiny grain of scientific plausibility and where the reasoning goes off the rails. Because understanding why certain ideas are appealing, even when they're probably wrong, is itself a valuable exercise. Let's start with the sun's rotation. The sun rotates, and it doesn't rotate uniformly. But as seen from Earth, the apparent rotation period is about 27 days. This means active regions on one side of the sun will rotate out of view and then reappear on the opposite side about 2 weeks later. So, if there were major active regions on the far side in late October, capable of producing multiple large CMEs, those regions should have rotated into Earth-facing view sometime in mid-November. Did they? This is something we can check. Next, lunar tides. Can tides trigger earthquakes? Actually, there's some evidence, but it's very subtle. Studies have found weak statistical correlations between tidal stress and the timing of earthquakes. The idea is that tides don't cause earthquakes, but in regions where a fault is already close to failure, the small additional stress from tides could be the last straw. Now we have 3 separate pieces. 1. Active regions rotating into Earth view producing CMEs. That happens regularly. 2. CMEs causing geomagnetic storms, also well documented. 3. Geomagnetic storms triggering earthquakes, not supported by mainstream science. Correlations, if any, are weak at best. No plausible physical mechanism. 4. Moon modulating earthquake timing. Very weakly supported. The claim, then, is that all of these factors converging at once could create a perfect storm increasing earthquake risk. And I have to be honest, when you stack that many weak correlations and speculative mechanisms on top of each other, the compound probability of the whole chain being real becomes vanishingly small. But here's why I think this narrative is appealing to some people. Despite the scientific problems, it creates a storyline, a causal chain connecting cosmic events to terrestrial consequences. It gives human significance to an interstellar visitor It taps into ancient intuitions about celestial omens. This is where scientific literacy becomes crucial. Geomagnetic storms are real. They are real hazards. A strong enough storm, like the Carrington event of 1859, could cause billions of dollars in damage to power grids and satellites today. Monitoring solar activity is important work, but conflating legitimate space weather science with speculative earthquake triggering doesn't help. It muddies the waters and undermines public trust. So, my position is this. Yes, let's monitor solar activity. Yes, let's track geomagnetic storm forecasts. But let's be very careful about drawing causal connections without solid evidence. And 3I Atlas's role in all this? The idea that an interstellar comet, a few km across, could trigger solar eruptions that affect Earth is, to put it mildly, a stretch. The energy scales don't match. The Sun is vastly more powerful than any small body passing through its vicinity. If 3I Atlas is electromagnetically interacting with the Sun, which itself is speculative, those interactions would be local and small-scale, not enough to fundamentally alter large-scale solar activity patterns that would affect Earth. So, while the narrative is dramatic, the science supporting it is thin to non-existent. We've covered a lot of ground, from orbital mechanics, plasma physics, to speculative hypotheses. Now let's bring it back to practicalities. What actually happens next with 3I Atlas? What can we observe, and what should we be watching for if we want to see whether any of these wild ideas have merit? First, let's establish where it is. 3I Atlas reached perihelion, its closest approach to the Sun, on approximately October 29th, 2025. After perihelion, the object is now moving outbound, traveling away from the Sun along its hyperbolic trajectory. It's already passed Earth's orbit again, heading out toward Jupiter's orbit and beyond, fading as it gets farther away, and the solar heating decreases. This means our observational window is closing. The object is getting fainter every day. The coma that made it easier to detect is probably shrinking. Ground-based telescopes and space telescopes can still track it, for now, but within weeks or months, it will become too faint for all but the largest telescopes. By this time next year, it will likely be beyond practical observational reach. This is the nature of interstellar objects. We get one brief chance to study them as they pass through, and then they're gone forever. So, if we want to learn more, we need to act fast. What observations should be prioritized? High-resolution imaging to get better constraints on the nuclear size. Continued spectroscopy to monitor how the coma composition changes as it cools. But one critical observation would be precise astrometry over the coming weeks. If there was any deflection from CME impacts, and continued tracking should reveal it, as the object's position progressively deviates from the pre-perihelion ephemeris. The deflection would compound over time, making it easier to detect after perihelion than during the coronagraph observations. If independent observers, now that the object is out of the Sun's glare, find that 3I Atlas is exactly where the original orbit predicted, that strengthens the case that no significant deflection occurred. If they find a deviation, that's extremely interesting and demands explanation. There's also the question of the Sunday. If active regions from late October have rotated into Earth-facing view and are still active, we should see them in current solar imagery. Sunspot groups are tracked and numbered. We can check whether any major groups appeared in mid-November. That could plausibly be the ones from the far side in late October. Looking further ahead, what happens when we detect interstellar object number 4? We will detect more. That's essentially certain. Improved survey telescopes like the Vera Rubin Observatory will dramatically increase our ability. We could be discovering multiple interstellar visitors per year. Each new detection is an opportunity to test our understanding. If the next object shows electromagnetic anomalies, that would suggest 3. I Atlas wasn't unique. If the next several behave conventionally, that would suggest 3. I Atlas was just a rare edge case. There's also the possibility of a dedicated mission to an interstellar object. Proposals for rapid response missions have been discussed for years. The technical challenges are immense. You need to detect the object early enough. You need a spacecraft that can reach extremely high velocities. But it's not impossible. If an interstellar object were discovered, while still beyond Jupiter's orbit, a mission could potentially be mounted. Such a mission could carry instruments to measure magnetic fields, plasma properties, composition, internal structure, all the things we can't reliably determine from Earth. It would definitively answer many of the questions we're grappling with now. Let's shift gears slightly. Let's talk about something that's been happening simultaneously with the 3I Atlas story, but in a completely different corner of astronomy. Because while we've been tracking this interstellar visitor, the James Webb Space Telescope has been quietly revolutionizing our understanding of exoplanet atmospheres, and one recent discovery connects thematically to what we've been discussing about unusual chemical compositions. In early 2025, JWST observations revealed an exoplanet orbiting a star about 200 light-years away, with an atmosphere that doesn't make sense according to our standard formation models. The planet is roughly Neptune-sized, orbiting in the habitable zone where liquid water could exist. But the atmospheric spectroscopy shows something unexpected. The atmosphere is dominated by carbon dioxide, at levels far higher than models predict, with very little water vapor. This matters, because when we build models of how planets form, we use our solar system as the primary template. An atmosphere rich in carbon dioxide, but poor in water, suggests formation in a region or under conditions very different from what we see here. Now, connect this to 3I Atlas. We have an interstellar object with a coma unusually rich in carbon dioxide, different from typical solar system comets dominated by water ice. Both the exoplanet and the interstellar comet are showing us that carbon dioxide can be more important in some cosmic environments than our local experience suggests. This tells us something profound about the diversity of planetary systems and the objects they produce. Perhaps systems forming from molecular clouds with different carbon to oxygen ratios produce objects with different volatile inventories. JWST has opened a new era in understanding planetary diversity. We're finding planets with atmospheric compositions that don't match anything in our solar system. And here's the connection. If we're seeing that much diversity in bound planets, imagine the diversity that exists among the ejected objects wandering between stars. Every planetary system probably produces millions of comets during its formation. A fraction of those get ejected into interstellar space, carrying chemical signatures from their birth systems. 3I Atlas might be a sample of a planetary system formed from unusually carbon-rich material. Its CO2-rich coma could be telling us about the chemical conditions in a stellar nursery that existed billions of years ago. It's a flying archive of extraterrestrial chemistry, and we have this brief opportunity to read what it contains before it vanishes into the darkness. This is why spectroscopy of interstellar objects is so valuable. Each object is potentially unique, and as JWST continues discovering exoplanets, we're building a broader context. The future of this field is incredibly exciting. We're going to discover more exoplanets. We're going to detect more interstellar objects. And gradually, we'll build up a catalogue of chemical diversity spanning the galaxy. And maybe, just maybe, we'll find evidence of truly exotic chemistry, molecules, or isotopic ratios, suggesting formation under conditions we've never imagined. While we've been focused on 3I Atlas, the Sun itself has been putting on quite a show. Solar Cycle 25, which began around 2019 and is projected to peak around 2025, has been more active than initially predicted. And in mid-2025, we witnessed one of the most powerful solar flares in decades. An X-class flare erupted from an active region on the Sun's eastern limb and sent a massive CME racing through the inner solar system. This event is worth discussing because it illustrates just how dynamic and unpredictable the Sun can be. Even with our sophisticated monitoring and modeling capabilities, the active region that produced this extreme flare didn't look particularly large or complex when it first rotated into view. Solar forecasters assigned it a moderate probability. But as it evolved, magnetic flux continued emerging from below, building up energy in twisted and sheared magnetic structures in the corona. And then suddenly, magnetic reconnection triggered, the stored energy explosively released. The flare itself produced an intense burst of X-rays and extreme ultraviolet radiation, causing radio blackouts on the sunlit side of Earth. The associated CME, traveling at over 2,000 kilometers per second, reached Earth in less than 24 hours. Unusually fast. When it hit our magnetosphere, it triggered one of the strongest geomagnetic storms in recent years, with auroras visible far south. Satellite operators reported anomalies. This event reminded everyone that we're still vulnerable to space weather. The Sun is not a stable, predictable object. It's a roiling ball of magnetized plasma, with internal dynamics we still don't fully understand. Our models can predict general trends, but they can't tell us when a specific active region will explode. Now, connect this to the 3I Atlas story. If the Sun can produce unexpectedly powerful eruptions from active regions that looked relatively benign, is it really so implausible that far-side active regions could have produced 3 large CMEs in rapid succession in late October? The answer is no, it's not implausible. The Sun is perfectly capable of doing that. The question isn't whether the Sun can do it. The question is whether those eruptions actually occurred and whether they actually intersected 3I Atlas's path. The increasing solar activity also means that space weather hazards are growing as we move towards solar maximum. More CMEs will be launched. More geomagnetic storms will occur. This is the natural rhythm of the solar cycle. It has nothing to do with interstellar objects or lunar phases. It's the Sun doing what the Sun does. But who knows? Maybe the data collected during this active solar period will shed light on exotic phenomena, like potential interactions with passing interstellar objects. The more we observe, the better our models become. Here's something that connects to our 3I Atlas story in an unexpected way. The increasing role of artificial intelligence and machine learning in astronomy. Because whether we're talking about detecting faint comets in coronagraph images, forecasting solar eruptions, or predicting plasma tail behavior, machine learning is becoming an essential tool for handling the massive amounts of data modern telescopes produce. Consider the detection problem. Coronagraph images are complicated. You have the bright corona, CME structures racing outward, cosmic ray hits, instrumental artifacts. Finding a faint comet in that mess is like finding a specific snowflake in a blizzard. Traditional image processing can do it, but it requires careful tweaking and human judgment. Machine learning offers a different approach. Train a neural network on thousands of coronagraph images containing known comets. Teach it to recognize the patterns that distinguish real objects from noise, and then let it analyze new images automatically. Several research groups are developing exactly these kinds of tools. Machine learning algorithms that can detect CMEs in solar imagery classify active regions by their flare potential. In early 2025, one research team published results from a machine learning model that predicts CME arrival times and speeds based on coronagraph observations. Combined with background solar wind conditions, the model was trained on decades of historical data from spacecraft like SOHO and Stereo. The result? A forecasting tool that outperforms traditional physics-based models in certain conditions. Now, imagine applying such a tool to the 3I Atlas situation. You could input the known orbit, the estimated Comet properties, the dates and characteristics of the alleged CMEs, and simulate whether those CMEs would have intersected the object and what deflection you'd expect. You could vary the parameters, exploring thousands of scenarios. The machine learning model could identify which combinations of parameters are consistent with the observed lack of deflection and which scenarios require fine-tuning. This is how you turn speculation and back-of-the-envelope calculations into testable science. The exciting thing about machine learning is that it can discover patterns humans might miss. Neural networks are good at finding correlations in high-dimensional data where human intuition fails. But there's a caution here too. Machine learning models are only as good as their training data. If you train a model on solar system comets and then apply it to interstellar objects that might have fundamentally different properties, the model might give misleading predictions. If your training data doesn't include examples of electromagnetically anomalous objects because they're rare or unprecedented, the model won't recognize them when they appear. Machine learning is powerful, but not magical. It extends our capabilities, but doesn't replace the need for careful observation and critical thinking. In the future, as we detect more interstellar objects, machine learning will play an increasing role. We'll develop models that can quickly assess whether a new object is likely to behave conventionally or show anomalies. We're not quite there yet, but when you combine machine intelligence with human curiosity, that's when breakthroughs happen. That's how we'll solve mysteries like 3I Atlas, by bringing all our tools to bear and refusing to be satisfied with easy answers. Let's talk about something that might seem unrelated at first, but connects thematically to our discussion of interstellar visitors and what they can teach us. That is, recent findings from asteroid sample return missions that revealed shocking properties about the internal structure and composition of small bodies. In late 2024 and early 2025, scientists analyzing samples returned by OSIRIS-REx from asteroid Bennu published startling results. The samples contained a higher proportion of hydrated minerals than expected, evidence of extensive water-rock interactions, but more surprisingly, they found tiny inclusions of highly reflective material, possibly metal-rich grains, distributed throughout. Detailed analysis suggested these inclusions had unusual elemental ratios. The point is, even asteroids, which we tend to think of as simple, primitive bodies, can have complex histories and heterogeneous compositions. The Hayabusa 2 mission samples from asteroid Ryugu told a similar story. Internal heterogeneity. These asteroids aren't just uniform piles of rubble, they're geological archives, recording billions of years of processing. Now, extrapolate this to interstellar objects. 3I Atlas has been wandering the galaxy potentially for billions of years. It's been exposed to cosmic rays. It may have passed through interstellar clouds. All these processes could modify its structure and composition in ways that solar system objects never experience. So, When we try to estimate 3I Atlas's mass and density from limited photometric observations, we're making assumptions based on solar system comets and asteroids. But what if those assumptions are wrong? What if interstellar objects routinely have internal structures that are more heterogeneous, or density profiles that are different? This connects to another recent finding: the analysis of pre-solar grains in meteorites, tiny dust particles formed around other stars before our solar system existed and got incorporated into primitive meteorites. They're identified by their unusual isotopic ratios that don't match solar system material. When analyzed, these grains show evidence of formation around specific types of stars. The exciting thing is, these presolar grains are microscopic samples of interstellar material, and they show that material from different stellar environments has recognizably different properties. This means if we could analyze a sample from 3I Atlas, we might be able to determine what type of star system it came from based on its isotopic fingerprint. Unfortunately, we can't collect a sample. The object is too far away and moving too fast. But we can do spectroscopy. High-resolution spectroscopy can measure isotopic ratios for abundant molecules like carbon dioxide. If 3I Atlas has unusual carbon-13 to carbon-12 ratios, that would tell us something about its origin environment. The sample return missions are teaching us that even relatively nearby objects are more complex than we assumed. Interstellar objects are likely to be even more surprising. We've journeyed through orbital mechanics, plasma physics, solar dynamics, exoplanet chemistry, and sample return missions. We've examined claims ranging from solidly established to wildly speculative. Now, let's step back and look at the bigger picture. Because the story of 3I Atlas, regardless of how it ultimately resolves, is part of something larger happening in astronomy right now. We're living through a revolution in our understanding of the universe, driven by new instruments and new techniques, revealing phenomena we never knew existed. 20 years ago, we had detected only a handful of exoplanets. Today, we know of thousands, with incredible diversity. Interstellar objects were purely theoretical until 2017, when we discovered Oumuamua. Now, we have 3 confirmed visitors, and we're building the observational infrastructure to find many more. Gravitational wave astronomy began in 2015, with the first detection of merging black holes. Today, we routinely hear dozens of gravitational wave events per year, opening a completely new window on the universe. Fast radio bursts, FRBs, mysterious millisecond duration radio pulses, first discovered in archived data in 2007, are now detected daily. All of these disparate fields share a common theme. We keep finding things that don't quite fit our existing categories, objects and events that sit at the boundaries of our theoretical frameworks, challenging us to expand our thinking. Oumuamua doesn't fit neatly into comet or asteroid categories. Some exoplanet atmospheres don't match our formation models. And 3I Atlas's behavior doesn't seem to fit our standard solar interaction models. This is a pattern throughout the history of science. When we develop new instruments, allowing us to observe previously inaccessible regimes, we almost always find surprises. Radio astronomy revealed quasars and pulsars. X-ray astronomy revealed neutron stars and black holes. Every time we open a new window, nature shows us something we didn't predict. 3I Atlas fits this pattern perfectly. It's an object we could barely detect a few years ago. Observed with instruments, pushing the limits of what's technically possible, showing behavior that might or might not challenge our standard models. It represents the frontier, the edge of what we know and understand, the place where science makes progress. By confronting anomalies and refusing to look away. Now, most anomalies turn out to have conventional explanations once we understand them better. Pulsars seemed weird at first. People joked about little green men signals, but they turned out to be rotating neutron stars with powerful magnetic fields. Exotic, but natural. Oumuamua's acceleration probably has a natural explanation involving outgassing or unusual shape. And 3I Atlas's resistance to deflection probably has a natural explanation involving measurement uncertainty or conventional physics we haven't properly accounted for. But the process of investigating anomalies is never wasted. Even when the answer turns out to be mundane, we learn something. We improve our models, we refine our measurement techniques, and occasionally, very occasionally, an anomaly turns out to be genuinely revolutionary, something that forces us to rewrite textbooks and rethink fundamental assumptions. You never know in advance which anomalies are which. You have to investigate all of them seriously to find the rare ones that truly matter. So, here we are, with an interstellar visitor that might have shown unusual electromagnetic interaction, or might just be a normal comet that we're overinterpreting due to limited data. The scientific process eventually will sort it out. More observations will be made. Better analyses will be published. The truth will emerge. Messy and uncertain at first, then gradually coalescing into consensus as evidence accumulates. What can we take away from all this? First, the universe is full of wonders, more diverse and strange than we imagine. Second, interstellar objects are valuable probes carrying information about distant stellar systems. Third, space weather is real and important, affecting our technology. Fourth, the tools we're developing are giving us unprecedented ability to study these phenomena. And fifth, maintaining curiosity while exercising skepticism is the right balance. Whether 3I Atlas short-circuited the sun or not, whether it's a dense planetary fragment or a fluffy comet, it has already served a valuable purpose. It's made us think, question, calculate, and wonder. It's inspired discussions that might lead to new insights, even if the original hypothesis is wrong. It's reminded us that the cosmos is vast and full of objects wandering through the darkness, occasionally passing close enough for us to glimpse them briefly before they vanish forever. So, keep watching the skies, keep supporting astronomical research, keep asking questions and demanding evidence. Keep that sense of wonder alive, that feeling of standing on a tiny planet, looking out at a universe that is stranger and more magnificent than we can fully comprehend. Because somewhere out there, right now, another interstellar visitor is on its way. Another cosmic mystery is waiting to be discovered, and when it arrives, we'll be ready with our telescopes, our equations, and our insatiable curiosity to decode whatever secrets it carries from the darkness between stars.